Welcome back to the channel. Apple II compatible wire-by-wire build. The address bus part 2. Presented by me, Dr. Matt Regan. And a little bit of a warning, for those new to computer architecture, this will probably be the trickiest part of the build. The aim of this playlist is to show the build for this board. It's an Apple II compatible, and it uses a 65C02 microprocessor. The idea being to show how the microprocessor works in the context of a system. I've used an Arduino Mega connected to a PC for display, keyboard and floppies. I want to give you a sneak peek at the next playlist. This is pure Turing. Now it's a little bit of play on words because there's no such thing as a perfect Turing machine. It's a breadboard based TTL Turing machine which emulates the 6502 one bit at a time. And in this clip it's actually executing the code for Apple Pac-Man. It's a proof of concept machine, and it's very slow, but I'm still amazed that an architecture this simple can execute 6502 code. And don't worry, I'll go over Turing machines in a lot more detail in the next playlist. So I want to go back to the ducks in pigeonholes, and remember that we start numbering the pigeonholes from 0. Remember that I'm using this as a metaphor for how computer memory works. Please watch how the CPU interacts with memory. And yes, I'm going to keep playing this at the start of each video until it's so obvious to you, you'll want to fast forward past it. Note the set of blue wires between the CPU and memory. That's what we're building in this set of videos. I've included both read-only memory and random access memory in this build, and the main justification I've used is that the Apple does it. So now I want to explore the difference between these in a bit more detail. There are really two big differences between ROM and RAM. The first has to do with what happens when the power is turned off. And we all know that computers are designed to do this just after we've typed in a massive file before we save it. Watch this and see if you can figure out the difference. What do you notice? Well, the RAM loses its data when the power's turned off, while the ROM retains its data. Let me play that again. The other difference between these memory types is given by the name, read-only memory. In this circuit, we can only read from the ROM but not write to it. Here, look what happens when I try to fill the memory with blue ducks. The RAM gets filled, but the ducks just won't stick in the ROM. I'll play that again. By now, you might be wondering how can we use these two different memory types together in the one build, and the answer is called memory mapping. This is where we arrange it so that some pigeonholes are pointing towards the RAM and some pigeonholes are pointing towards the ROM, and we use the pigeonhole address number to determine which we use. One more time. So, what happens when we turn the power off? The ROM is preserved, but the RAM is cleared, which we kind of expected. But now what happens when we try and read from the memory? Reading from RAM works as normal, and reading from ROM works too. We can write values into the RAM, but when we try to write the duck color into the ROM, it just fails. Just to summarize memory mapping, we use the address to determine functionality. In this case, the lower addresses select for the RAM, and the upper addresses select for the ROM. How do we do this? Well, first we wire all the data lines and all the address lines of the ROM and RAM together. And note that I like to use red for data lines and blue for address lines. Both the ROM and the RAM have a signal called chip enable, and the chips are only active when this signal is set to 0 volts. If the chip detects 5 volts on this wire, it goes into its idle mode. In this build, we should never have the chip enable of both the RAM and ROM at 0 volts at the same time. So we want to use some logic to look at the address to decide which chip we want to enable. And usually we don't need to look at all 16 lines. In fact, here we just need to look at the upper 2 lines. Then we connect the memory to the 6502 as normal. Now the Apple II also connects to some other devices, such as the display, the disk drive, and the keyboard. For the display, the 6502 just reads and writes to RAM as normal, and some extra hardware in the background reads this RAM and sends this information to the display. As I said earlier, this is the main reason I want to use the 65C02, which allows the video circuitry to have access to the RAM. But other devices, like the keyboard and the disk drive, have some dedicated memory addresses assigned to them. When the 6502 reads or writes to these dedicated addresses, it thinks it's accessing memory, but in fact, it's talking to these devices. To go into memory mapping in a bit more detail, I need to introduce another topic.
Hexadecimals to the rescue.
Now that scene in The Martian is just a direct tribute to we computer nerds. If you remember back to the introduction video, you'll remember I used these rotary dials. Each dial can encode one digit with a number between 0 and 9. This is called binary coded decimal. But there are some combinations left unused. And in general, we want to use all the address space available, so we label these extra combinations A through F. And this is hexadecimal. This covers all the possible voltage combinations on 4 wires. The 6502 has 16 address wires, which means we have 4 hexadecimal digits. 0101 is 5, 1001 is 9, 0111 is 7, and 0010 is 2. So we call this address 5972. The next example is D50F, and here's 91CE. And here's the important address for this build, C000, which we often just refer to as C1000. For this number, we normally leave off the leading zeros, just like we do in decimal, and just call it 5F. And finally, the biggest number possible, FFFF. Let's have a look at the published memory map for the Apple II. Location 0 through BFFF is used for RAM, and the video memory is located within this. The address range from C1000 to CFFF is used for I/O, and D1000 to FFFF is usually used for ROM. The keyboard itself uses addresses C1000 and C010. And for the video, while the image to be displayed is held in the main RAM, the mode itself, such as text or high res, is set by reading or writing values in the low C1000 range. Note that there's a pretty big gap between the 70s definition of high res and our current definition of high res. Thank you, Moore's Law. And finally, the floppy drive, which uses some specific addresses between C0E0 and C0EF. So we see that the keyboard, video mode, and disk drive all use this range of C1000 to C0FF. And so what we need is some special hardware to decode addresses between C1000 and C0FF and tell the Arduino to take control. What we really want is a circuit that can detect this combination of ones and zeros in the upper lines of the address bus. Specifically, when A15 and A14 are both at 5 volts, and A8 through A13 are all at 0 volts. To do this, I'm going to have to introduce another logic gate. This time, the AND gate, which has 2 or more inputs and 1 output. This is a 2-input AND gate, and the output will be at 5 volts only when input M and input N are at 5 volts. Otherwise, the output will be 0 volts. We can easily extend the concept out to 3 inputs. Here, input M, N, and P have to be at 5 volts for the output to be at 5 volts. Again, otherwise the output will be 0. You might notice that I'm using the term 5 volts and the binary level 1 interchangeably. But in this case, I want to detect when some of the inputs are high and some of the inputs are low. So how do we go about doing that? High meaning 5 volts, and low meaning 0 volts. Well, there are 8 wires I'm interested in, so I need an 8-input AND gate. And again, the output will only be at 5 volts when all of the inputs are at 5 volts. Otherwise, the output will be 0. So for some of the signals, I need to invert them before they go into the AND gate. That way, the AND gate will actually detect when they're 0. But I still have a problem. If I look up my trusty 7400 series logic chips, I can see that there's only an 8-input NAND gate. So what's a NAND gate? A NAND gate is a variant of the AND gate, which has an inverter in front of it. The output of the NAND gate will be 0 volts only when all of the inputs are at 5 volts. Otherwise, the output of the NAND gate will be 5 volts. Back to the circuit. I can use an 8-input NAND gate, it just means the signal I want will be inverted. Remember I installed another part at the start of this address bus build? Well, that was in fact an 8-input NAND gate. specifically the 74HC30. Now the last thing I need to do is wire in the logic for selecting the ROM or the RAM. Now below C1000, I want the RAM to be selected for reading and writing. Above C1000, I only want the ROM to be selected when both the C0XX bar and the read-write bar signals are high. I can get this behavior by first using two NAND gates connected to the two upper address lines, and using this to select the RAM for addresses below C1000 and the ROM for addresses above C1000. When A14 and A15 are both at 5 volts, the output of the lower NAND gate will be 0, which will select the ROM and deselect the RAM, and all other combinations will have the opposite effect. Then I use another NAND gate connected to the output enable pin of the ROM to tell the ROM only to output when both C0XX is high and the read-write signal is high. The net effect is that the ROM will only output for reads above C100. Alright, that wraps up the theory section for this video. Now on to the practical part. The remainder of this video will be the build. And that's about it for the address bus. Next video will be the control bus, and then after that, we'll actually try and get this puppy to work. Press the notification bell to be informed when the new videos are available. Don't forget to like, subscribe, and share, and I'll see you in the next video.